Welcome back, dear participants. So now I welcome Dr. Mayalagan from Department of Chemistry to chair this session and introduce the speaker. So now the stage is to Dr. Mayalagan.
Thank you, Dr. Kamala Bharati.
Yes, sir, please proceed.
It's a great pleasure in welcoming Professor Ramasamy Murugan. To give a talk in faculty development program on novel materials organized by Nanotechnology Research Center. Professor Ramasamy Murugan is currently working as a professor in the Department of Physics, Pondicherry University. Earlier, he has worked as Director UPSC, Department of Science and Technology and Environment, and also worked as a visiting scientist at the University of Texas, Austin, and also Shizuoka University, Japan, and Nagoya University, Japan, and as guest researcher at University of Kiel, Germany. And his research is focused on the design, synthesis, and characterization of functional materials with an emphasis on understanding their intimate structure property interplay. His major contribution is the invention of zirconium containing lithium garnet oxide as electrolyte for all solid-state lithium battery. And he was privileged to work with world-leading researchers. Professor John Goodenough is a Nobel laureate in 2019 from University of Texas, Austin, USA, and Professor Werner Webner, University of Kiel, Germany, and Professor Robert Huggins, Stanford University, and University of Kiel, Germany, in developing the high energy density batteries. He is actively working with Indian industrial partners like Corning USA, Flisker USA, Applied Materials USA, and HPL Hyderabad through sponsored research and consultancy projects to address some of the challenges in the realization of lithium battery technology for electric mobility and consumer electronics. Currently, he is serving as editorial board member of the journal Ionics, published by Springer, and also he is a co-editor of journal Current Smart Materials, published by Bentham Science, and also is a president of Energy Science Society of India. He was honored as a fellow of Royal Society of Chemistry, fellow of Academy of Sciences, Chennai, and member of American Chemical Society through invitation, and several research awards by UGC and India, and also recently has got the top 2 scientists person in the world, and he is among the 3% in Pondicherry University to be the top 2% in the world. And I welcome you, sir. It's a great privilege to welcome you and give you a talk on inclusive insights and outlook towards practical solid-state batteries. Welcome you, sir.
Dr. Mayalagan, thank you very much for your kind words and the nice introduction, because mostly. So I am happy to be here and also thankful to Kamala Bharati. I think Kamala Bharati, can you give a permission to share my slides?
Yes, sir. Yes, sir.
I think somebody is most disabled participants screens sharing. Yeah, thank you. I think it's now right.
Yes, sir.
So now, Mayalagan, can you see my PowerPoint?
Yes, sir. Yes, sir. It's visible now.
That's okay. Once again, thanks a lot for the organizers and Dr. Mayalagan and the Kamala Bharati. So I will take another 1 hour for the discussions. It's like a storytelling. I don't want to discuss too much on the advanced aspects, because it's a faculty members. I want to discuss in very simple manner. I think mostly in storytelling manner. I don't want to give too much on the advanced topic. But I thought that most of you are having background of material science. So if you have any doubt or if you want to discuss something, you can stop at me in between. Nothing wrong in it. Okay. So idea is just I wish to discuss on the inclusive insights and outlook towards practical solid state lithium batteries. So this is regarding evolution of energy storage devices. Look into this from 1800 Voltaic file to today 2020. I think for the last 2 centuries, a lot of progress has been made towards the realization of the electrochemical energy storage devices. Presently, we are focusing on the micro battery or the pacemakers, and for the e-mobility and for spirit storage. I think a lot of people are working on flexible batteries. But still, we have to think about what else, what is for the next generation battery is concerned. So if you ask me, next generation battery, it should be a lithium metal based batteries, because we can think about the highest energy density only with the lithium metal. Then you can ask me, because almost for the last 30 years we are surveying with the present lithium-ion battery technology, what is the necessity for moving towards the new technology or something new generation of batteries? Particularly, we are happy with the lithium-ion battery technology, which has been introduced in the 1980 concept and commercialized by Sony after some time. If you ask me, the current lithium-ion battery technology is concerned, just you are having graphite is the anode, and maybe you can call it as the cathode is the lithium cobalt oxide, and non-aqueous liquid electrode. You can think about the output voltage something around 3.6 volt. Quite good. It's the intercalation and de-intercalations. You know very well that how you are charging and discharging. You are using almost in all the type of portable electronic devices based on this type of battery. So if you look into the present lithium-ion battery technology replaced by all the commercialized products, more or less very similar with these ones. Maybe they will change little amount of the composition of the electrolytes, or they will reduce the thickness of the separators, or slight changes. Maybe instead of lithium cobalt oxide, people have gone to lithium iron phosphate or NNC, NCA or something else. But chemistry is almost same for the past from 1980 to 2020, almost 40 years. There's no dramatic change in the chemistry behind this present lithium-ion battery technology. Why we require a new technology? What's the problem with the existing technology? So if you look at the disadvantage of present lithium-ion battery technology, safety concerns, potential electronic short circuits of electrodes, that's a major problem. And formation of reaction product lines at the electrode-electrolyte interface is another problem. Since it's the organic liquid electrolytes, leakage due to use of liquid electrolyte is another major problem. Above all, the great restriction in achieving higher energy density batteries with the present battery technology. That's the reason why people really struggle hard to improve it. I think credit should go to good enough, because we are surviving this technology and chemistry just because we proposed this technology. The challenges means, if you ask me, electrolytes, development of non-flammable electrolyte with a larger window between its lowest unoccupied molecular orbital, what we call LUMO, and highest occupied molecular orbital. So we have to think about developing a non-flammable electrolytes with a large potential window. When you're developing these non-flammable electrolytes, you have to think about this conductivity also. Lithium-ion conductivity should be greater than 10 power minus 4 Siemens per second. And conductivity across electrode-electrolyte interface is also needed. That's a very difficult task. This is regarding electrolyte. An electrode to design better anode than carbon or graphite. It's very difficult task. People are struggling hard moving towards silicon and other aspects. Still, it's going on. Nothing for their new anode. To design a cathode composed of environmentally bending, low-cost material that has its electrochemical potential well matched with the home of the electrolyte and allow access to 2 lithium atoms for transition metal cation to increase the energy density. It looks very simple, but allows 2 lithium atoms for transition metal cation. So in tough jobs, we have to look into the new cathode material. These are the challenges to realize a really high energy density batteries. If anyone want to focus on electrolytes, he has to think about of developing a non-flammable electrolyte with good ionic conductivity. And electrodes anode means if you don't want the carbon, then you have to think about something. Then cathode also, you have to think about can assess two lithium atoms for transition cation, just to increase the energy density. So these are the three ways of working on overcome the challenges in lithium battery technology. Why we require these ones? If you look into the present lithium-ion battery technology, the maximum limitation is something around 210 watt-hour per kilogram. If you really want to run your electric vehicle, particularly car or bus, I think we have to match with what we are having present technologies, IC engine technology, the gasolines, which are also something about 700 watt-hour per kilogram. So we have to think about increasing energy density from this level, maybe around 120, 140, or 160 watt-hour per kilogram to something around 600 or 700 watt-hour per kilogram. And only you can climb now achieve a really high energy density batteries by means of it, almost everything you are interested. That's why people are working hard how to improve the energy density, not at the cost of safety of the battery. So people knows very well that. Lithium metal is ideal choice because it has 10 times the theoretical specific capacity of the carbonate, lithiated carbon. Lithiated carbon something around 372 milliampere hour per gram. But if you're able to use lithium metal instead of lithiated carbon, we can think about reaching something around theoretically 3,860 milliampere per hour. So in this case, 10 times from 370 to 3,860. And much more, lithium metal has the low density, highest negative electrochemical potential, minus 3.055 volts. We cannot think about. Hello? Murugan.
Yes, sir, please proceed.
Yes, sir, tell me.
Some problem, I think someone is muted. Let's check. If you have any trouble, you please inform. Okay. So cathode electrolyte and anode. So just at least people thought that since you can expect the large amount of energy, increase in energy density just by replacing the lithiated carbon, people thought that immediately why don't you use this best possible anodes, metallic lithium means. That's what people thought initially. So with the present existing lithium-ion battery technologies, everybody knows when you place these lithium metals highly reactive, can react almost everything. So dendrite is the biggest problem. So dendrites happens, I think in real times, what happened means it can immediately, it can short, then it starts to explode. Which means that with the existing technology, although lithium metal possesses a higher energy density possible, may not be in a position to replace the existing technology, the lithium electrolytes. But people don't want to give it up. So they thought that they want to use the metallic lithium. If you're able to use the metallic lithium, then we can think about at least 3 possible technologies. So with the existing electrodes, insertion electrodes, you can use them as a cathode, and lithium metal is anodes. That's one way. The another one is the lithium sulfur battery. And naturally, the final people imagine, let us go to the lithium oxygen or lithium atom battery. This is the people really want to achieve. But I don't think it's much easy to achieve. So lithium metal battery with intercalation cathodes will come across the low coulombic efficiency, short cycle lives, dendritic growth, lithium metal corrosions. Almost everywhere you can find these problems. So this comes just because of the lack of a suitable electrolyte is the major problems. We are having other problems, leave it. Only in the yellow if you circle, you can see almost all the technology requires a good electrolyte, then only you can imagine or you can think about fabricating and evaluating these 3 types of. So my idea is to focus at present lithium metal battery, then touch upon the lithium sulfur battery, A lithium ion battery is not that much matured. So we have to think about these two technology, these kinds. Then people start that if you really want to use the metallic lithiums, then we have to overcome this. We have to replace the liquid electrolyte by something else. That's why people use a lot of talk on the solid state batteries. If you look at the present lithium ion battery technology, they're using these porous negative electrodes and porous positive electrodes. In between is the ceramic separator, ceramic layer separator. Then you are having current collector. So as I told, is graphite is the this porous negative. And in this case, porous positive electrodes, lithium metal oxides. You can think about anything, lithium cobalt oxide, lithium iron phosphate, or NRC, NCA, whatever it might. Putting some polymeric binder, then completely a liquid electrolyte. Already we discussed, we want to replace this carbon by means of the metallic lithiums. So when I want to use the metallic lithium, I may not be in a position to use the present lithium ion battery with what you call the current organic liquid electrolytes. So I replace this carbon by means of the lithium. But if at all, if I want to use it, so not only these insertion electrodes, you can think about the all LCO, NMC, NCA, or air, or sulfur, anything, any X. So what I require is I wish to remove this what we call liquid electrolytes. I want to introduce these solid electrolytes. So metallic lithium is solids, then my composite cathodes is solid, and I want to replace the liquid by means of a solid electrolytes. Then I can say all solid state lithium ion battery. It looks very simple. So lithium is well known. At least you are having all the insertion electrodes and everything. So I told you for the bottleneck for the realization of this what I call lithium metal batteries, the electrolytes, particularly liquid electrolytes. I don't want liquid electrolytes. People thought that if anyone develops a solid electrolytes, then there is only possibility of increasing this incorporation of the lithium metal in the battery, and you can improve the energy density something around 10 times. That's the concept behind the all solid state lithium batteries. Then you can ask me, what if of solid electrolytes? I can leave it now. I don't want to discuss. I propose these three things. So if I able to develop this solid state battery, so I can completely avoid this what you call safety issues with the present lithium ion battery technology. You can see here, this is the present lithium ion battery technology. I'm removing this what you call the separator and as well as the liquid electrolytes. Then I can have the lithium iron phosphates. I can reduce the volumes. Then instead of the insertion electrodes, I can think about the sulfur. I can think about the oxygen also. The greatest advantage is the volume advantage. I can reduce the thickness and it's one flavor. That's the idea behind of developing this solid state battery. If you ask me what are the advantages of solid state batteries? It's a simple structure. So I don't require a separator. Solid electrolyte itself plays a role as separator. And if I'm able to develop a good solid electrolyte, if its chemical stability is quite good with the lithium metals, then I can think about enabling use of lithium metal as a conduit. Which means that since I'm able to use the lithium metal, I could improve the energy density. Energy density I could improve. Since I'm using a solid electrolytes, there is no need of cell grade or something else separator. And moreover, my solid electrolytes potential window is quite high. I can think about developing a battery 6, 7, 8, 9 volt also. So if you're able to improve the voltage, naturally it will help to improve the energy density. And non-flammable, mostly what you're thinking, solid electrolytes are much more better characteristics when compared to the liquid electrolytes. It's better non-flammable electrolyte. So I can think about using the solid electrolyte at high operating temperature. Particularly country like India, tropical countries where 60, 70 degree goes, so I can use it. Electrolytes flame retardant, no electrolyte leak, simple safety measures needed on the part. Which means that safety is quite good. Large operating temperature, I'm talking about the high temperature, right? And moreover, I need not spend so much money on the what you call battery management is concerned. So it's nothing but three solid materials. Cathode is solids, electrolyte is solids, and what he call this anode is lithium metal is solids. So simple structure and simple manufacturing process. That's what people thought that reduce the cost at the large scale. So these advantages makes people to think about why don't we spend so much money on R&D activities on the what you call solid state batteries. So everything depends on finding a suitable solid electrolytes. So if you want to realize solid state battery, particularly the lithium metal is the anode, then you have to develop a solid electrolyte which should possess at least these characteristics. Ionic conductivity at the operating temperature, not like a solid oxide fuel cells 700 degrees Celsius at the room temperature, that solid electrolyte should possess the good operating and the conductivity. It should be chemically stable in contact with the negative and positive electrode. There should not decomposition when it starts to react with metallic lithium or electrode. Positive electrode is considered. And above all, your electrolyte should be negligible absence of electronic conductivity, something around 0.99 transference number. Not only at the ambient condition, wide range of lithium activity and temperature, high electrochemical stability, and much more very important for the industrial point of view, your electrolytes should be low cost, safe, easy preparation, and again, you have to get the clearance from the pollution that's very easily environment friendly. So these are the characteristics you should think about before developing a solid. That's really a biggest important. Really, people struggle hard to find all good characters in a single material. But it's not new to the world. So 1800 Volta made this voltaic foil. 1839, Michael Faraday, the first solid state electrode is a lead fluoride. Of course, good conductivity at high temperature. In 1884, Wabach demonstrated the sodium ion conduction in glass. In 1888, the first measurement of transference number. In 1900, discovery of a next glower, a ceramic rod was heated to incandescent, that's what we call the latter solid oxide fuel cells, and oxygen gas sensors came into the picture. Great development in 1900. 1914 is a high silver ionic conductivity in the silver iodide at 150 degrees Celsius. 1966, a sodium sulfur battery by using a sodium ion conductors, sodium beta alumina. Then 73, Adnan made this biggest breakthrough of first polymer electrolyte. So which tells very clearly. So now we are living in the age of 2020, but solid electrolyte research started in 1839, just after 39 years of the world. So it's not new to the world. From 1839 to 2020, we are struggling hard to find a good solid electrolyte to satisfy those conditions. Then sodium chloride occurs. Ionic conduction liquid and solid, just for comparisons. So if you, that's a very common salt. Sodium chloride dissolved in water, the conductivity is something around 10 power minus 1 Siemens. The same sodium chloride in solid, that's a crystal, the conductivity is 10 power minus 12 Siemens per centimeter. Just imagine why people prefer this liquid electrolyte solution. Conductivity is so good. The solid is almost 11 times lower than the conductivity of this. Which means that, so if you want to make a device, the biggest bottleneck is the lithium ionic conductivity of this solid. So if at all you want to realize the conductivity, you have to lift it at least 10 power minus 3 Siemens per centimeter at room temperature. That's from 10 power minus 12 to the 10 power minus 3. Big thing. How do you improve ionic conductivity? Okay. If you look at the very basic equations, solid electrolytes in ionic conduction, the electrical conductivity depends on 3 factors. One is it sigma equal summation I, qi, mu I, charge in coulombs. I is the concentration of defects per ions, and mu is the mobility. So ionic conductors, so ionic species are the either it's a proton conductor, lithium ion conductor, sodium ion conductor, oxygen ion conductor, fluorine ion conductors. So cations and anions. So the defects, the doping or substitution. So addition of cations and anions creates defects. So when you're able to grade, that's very natural. It's a pure gold. I don't think a pure gold is useful for any ornamental purpose. You cannot make it anything. Ideal. But when you had a small amount of copper, then it's quite good. Characteristics has been changed, which is useful to be making ornaments or something else. Very similarly, a perfect crystals may not be useful, but when it starts to have a defects, then it starts to contribute. So addition of cations and creates a defects. So intrinsic disorder created by phase transition, that's what I call beta phase of alpha, beta to alpha phase of silver iodide, or sodium beta alumina amorphization. So this is space charge. Modification of charge at interface to balance opposite charge planes, that's what I call formation of diffusion zones, which improves conduction. Which means that the defects really helps to, so if you have the concentration of defects is larger, then every possibility that you can improve the conductivity. The mobility is so good that you can improve the conductivity. So defects means in order for an ion to move to a crystal, it must move from one occupied site to the vacant site. Thus, ionic conductivity can occur if defects are present. The two simplest types of point defects are the Schottky defect and Frankel defects. You might have seen the Schottky defect is the example sodium chlorides, sodium plus and chlorine minus, and sodium ion vacancy. The Frankel defects, you can see here. Similarly, vacancy conductions. So when you have a vacancy, then it starts to go from the one occupied site to the vacant site. From here to here, jump. So a cation and anion vacancy phase pass up here. So increase in defects helps to improve the conductivity. That's what I call Arrhenius relations as sigma to A exponential minus EA by RT, where EA is the activation energy. So energy required to what you call the jump from the occupied to the unoccupied. Energy is less than very fast lithium ion conduction. If you require very large amount of energy to jump, I think conductivity will come down. This is based on random walk theory. Just I'm giving the basics. So this is same thing on the Schottky defects. So what's the movement of sodium ions and sodium chlorides? By vacancies originating from Schottky defects. So which means that sodium ion must squeeze through the lattice, inducing significant logical distortion or relaxations. So if you're unable to cross that bottleneck, then factor that limits the mobility of ions. So if unable to jump, then it goes back to the original position, leading to no net ionic migrations. So transition state would determine the ease of migrations. So defects is essential if you really want to think about the conduction in the what we call crystalline material is concerned. Frankel defects in silver chlorides can migrate at two mechanisms, one by direct interstitial jumps and interstitial mechanisms. So here silver directly jumps to silver tube. So here it takes in this path. So not through the lattice sites. So whatever it might be, what you required is the zirconia, classic example of the oxide conductors. So vacancy is essential if you really want to think about the conduction in this type of the solid material. So that is regarding the defects. Then mobility, we're talking about MUI. So which got natural amplitude of energy barrier to shift from one side to other, here to here. This is energy required to jump from here to here. So structural geometry constraint to enter the site. Then electrostatic interaction with the neighboring heads, because this positive means what will happen, it will not give as much as forces. Then free volume ion size. Then polarizability of the lattice. So these are the factors which contributes a lot to the mobility of the ions are concerned. So which means that activation energy means how much energy you require to defects creation plus the migrations. That's what the people used to calculate the activation energy required for these conductions. Which means that the concept of material design should be high mobile ion concentrations, high number of empty or vacant sites for ion swapping, small activation energy for conduction, high number of conduction channels, high polarizability of framework of ions. So in general, amorphous materials will have much better conductivity. I don't want to this, but at least see. So these are the characteristics which makes you. So this is how people worked from 1839 to till date to get the best lithium ion conduction, what you call fast ion conduction. So people have to think about the carrier concentration, or what you call the defects. Ionic activity comes from the starting from here. Defects are diffusion pathway and diffusion time. So many mechanisms: vacancy, impurity, Frankel defects, Schottky defect, interstitial defects. These are the defects. So if you have the defects, then you have to think about the carrier concentration and carrier type. So anions, sublattice, the different closed pattern frameworks, this what you call designs and distribution pathway. So here, diffusion type. So people have developed this theory quite long times, and still they worked very hard to develop this what you call the ionic fast ion conduction in materials. So I will come back to the real picture. So we started with to develop the all solid state battery. We badly required a good fast lithium ion conductors. So this lithium nitrate is the best material they found out in the 1957, Li3N. Then 67 beta alumina, NRC and 10 power minus 4 conductivity at 1976. Like that, you can see this developments, evolution of these solid electrolytes. So looking through the solid electrolytes, I told you to possess high lithium ion conductivity, wide electrochemical stability, and good mechanical properties and simple processability. So I have to choose the best combination of all these things. Then I can claim I developed the ideal solid electrolyte. So people struggle to develop these ideal solid to find the material with all the required characteristics. So although we're having several classes of materials, so let us take the two important classes, what we call sulfides and oxides. So competitors for electrolytes for solid-state batteries. Sulfides, it's really quite good. If you ask me, the conductivity is so good, -2 Siemens per centimeter. Then compatibility with the electrodes are quite good. Wetting ability is so good. It has its disadvantages. Stability with metallic lithium is not so encouraging, and much more, it's very moisture problem. You cannot make this material at the open conditions. Special sample preparation chambers will require. And it's very, very, very difficult for bulk production. Although it possesses all the characteristics, but unfortunately for bulk production, which means that in an industrial point of view, it's very difficult to produce a battery electric vehicle. It means that sulfide is really a tough job as an electrolyte. Characteristics are good. Maybe button cells or what you call the cell for the pacemakers is ideal choice. But the industry wants to produce the cells in a big volumes. Then it's not the right material. That's why Toyota is spending so much money and long term of research. Really a worried lot in developing these. Actually, the pandemic really helped them to overcome because the challenge they promised they will run an electric vehicle all based on all solid state battery based on sulfides. Olympic. I think it's very big happy because Olympic will be taking place. But oxides, ceramics, people are having the quite long experience. And compared to the sulfides, it has its own advantage, mechanical stability. You can process it very well. So technology is well mature technology, oxides. Although the conductivity is poor and doesn't have much greater property compared to the sulfides, still a lot of focus on the oxides. Most of the ceramic people like this industry likes these oxides because very easily you can scale up the process. So if you look into these solid state inorganic electrolytes landscapes, Only sulfates is the best option, then maybe aramorites, and antiferrous was introduced by the particle Professor. Good enough, still he claims it's the biggest inventions, but a lot of controversy regarding antiferrous. Then perovskites, good conductor, unfortunately, a lot of grain bound resistance. And you are having a titanium which is not stable against metallic lithium, Nazic and Lisicans, offers life on many materials. But although we are having several family, unfortunately, nothing is so suitable for the bulk production or whatever disadvantages. It means that we have to think about of developing a solid electrolytes which is slightly better than these. So I told you we are much interested on the oxides. Let us compare only few materials, oxides. People thought that these four materials is highly suitable for developing or realizing the all solid state lithium batteries. The left hand side, just I've taken a 4 example. One is the Wakara sheets. Maybe you can take this the Zippo. Next is the Lipon. Then lithium, titanium, aluminum, germanium phosphates, or lithium, lanthanum, titanate, perovskites. So this is the conductivity map. So from this conductivity, it's very clear. Perovskites, lithium, lanthanum, titanate possess the maximized conductivity among 4. Next is this Wakara, lithium, titanium, aluminum phosphates made by this industry. Then Lipon, then Lisipo, lowest conductivity, and this lithium lanthanum titanate is highest conductivity among the 4 candidates. But we know very well that we are not only working on the conductivity, and if we have the conductivity, then we have to think about stability against metallic lithium. Here, if you see stability, the Lipon, 5.5 volts. So you can imagine making a battery with 5.5 volts large potential window. Lisipo also same. But unfortunately, the conductivity is very poor for Lisipo and Lipon. The lithium titanate, best conductivity, but the potential is 3 point, and moreover, titanium is the biggest, so it's very difficult to have the metallic lithium with titanium. Easily it can be reduced. And Wakara, this particle, people are working on this lithium, titanium, aluminum, germanium phosphates. This is also not so good. Anyone want to talk to me? Some noises are coming. Okay. So one thing is very clear. Material which possesses the good conductivity doesn't have the good electrochemical stability. Material which possesses the good electrochemical stability doesn't have the good conductivity. This is how God plays a biggest role in battery research. Particularly for battery research. If it gives one best property, it will pull down the remaining properties. So, which means that if at all, if you want to think about developing a true solid electrolytes for high power lithium battery, it depends upon the successful identification of suitable solid electrolyte with good lithium ion conductivity and good chemical stability. That's a bottleneck. So not only conductivity is useful, but at the same time you should have the good high electrochemical stability. So how to lift these two properties? That's a very, very, very interesting. That's the reason why from 1839 to 2007, people struggled hard to lift these two properties are concerned. So since I told you we are interested in the oxides, if you look into this earlier research, people tried so many oxide materials, perovskites, antiperovskites, Nazic and Lisicant structure. Which means that is the fast lithium ion conduction is limited only to the perovskites, antiperovskites, Nazic and Lisicant. Why people are struggling hard only with this structure? Can we think about some other structure which can really provide the good lithium ion conductivity as well as the good electrochemical stability? That's the question. So what is that? Just people started to realize, so it's time to think about the new structure. We have to think about look for the new structure. That's why to design a new solid lithium ion conductor for solid state batteries. So our group, particularly also reference groups, has also started to think about the new structure. They found this what we call the lithium garments. So credit should go to these Italian scientists and Japanese. So made this all pure structural inorganic chemistry. They are very much interested to make the materials and powder oxide fraction. They published the results. So it's a new compound. So like that, they found these lithium garnets, Li5, La3, M2O21 with niobium, tantalum, and antimonites. They synthesized a very simple techniques, and just by powder oxide effect, this could be a possible structure. Why our group is much interested is these compositions. Li5, La3, the best composition for us is the titanium. But titanium is the biggest problem. But this system is interesting. Instead of titanium, we are having niobium, tantalum, and antimony. So, which means that we can think about these materials are the fast lithium ion conductors. If at all these materials are fast lithium ion conductors, then we can think about of what we call the electrochemical stability. That's how the research started in 2004 or 5. So, before moving to lithium garnets, let us look at the ideal garnets and the lithium garnets. That's what the 88 purpose of the PM on AICTE, the structural chemistry proposed based on powder oxide fraction. If you look at the ideal garnets, you're having a C case, the perfect tetrahedral coordinations. But if you come back to the lithium garnets, the garnets, ideal lithium is occupying 2 distorted octahedral coordinations. It's completely occupied, but here it's at least one lithium is not completely occupied. You are having some packets. So, which made us to interest in this class of system is at least the people have reported there is a vacancy and it's not completely filled. So, since there is a vacancy, there is every possibility lithium can make a jump into these vacant sites, and there is every possibility we can realize this lithium ion conduction in these materials. This is how started. Then people. A group in Kiel, they started to prepare these materials like niobium, tantalum, and antimony. Just that focus on the niobium and tantalum. Initially, by means of solid state reaction, just mixing together at calcine at 700 and again wall milling, and just by heating at 950 degrees Celsius for 24 hours, they are able to synthesize this material. So, able to synthesize at 700 and no impurity phases, very good, able to reproduce. They then started to, because being electrochemist, our group is interested in the conductivity. So this is the impedance pattern of this Li5, La3, Ta2O12. They realized the conductivity is something around 10 power minus 6 siemens per centimeter. So our target is 10 power minus 3 at ambient conditions. So at least 3 order of magnitude higher. No need. Let us think about it. It's really interesting. So conductivity is good, not bad. That's the first positive. But they made instead of tantalum, they put niobium. They want to compare these two materials. Then niobium has the better conductivity compared to tantalum. Still, it's 10 power minus 6. So it may not be suitable for making solid state battery, but conductivity is quite good. Fortunately, this is an added class now with the family of the lithium ion conductors. Then, in the meantime, Stephen Adams, now he is in the University of Singapore. They want to understand what could be the possible lithium ion pathway for the lithium ion motions. Very interestingly, they are able to found that. Hello. Hello. Okay.
Sir, please go ahead. Please.
It's okay. So this is structure of the lithium. So just based on the possible available powder oxide fractions. So this group is very good in this bond valence analysis. So with the available structural powder oxide fraction, able to predict that very interestingly, it's a 3-dimensional path. It's not like a Lysican, 1-dimensional pathway for the lithium ion. It's a 3-dimensional. So this is really people want. So it's a lot of interest came to the one. Oh. Then I entered. The story is completely, I am not a solid state chemistry man. I'm basically a physicist working on Raman spectroscopy, 2 postdocs. Since I built a house, I want to relax for some time. That's how I entered into these rooms. While looking through the literatures, I found that there is a group in Professor Werner Wapner. Angadurai is working. He is my junior in the college. I never met him. Going to the CV, I found that he is in the University of Kiel. Just I expressed my interest because I wanted to carry out something on battery materials and I get some post. Interestingly, since I am the senior to him, because basically he is a chemist, I am the physicist. We studied in Sacred College. Somehow he also recommended Wapner is happy with my earlier publications in Raman spectroscopy. So the family entered into the what you call this process of development labs. At this juncture, I wish to tell you one thing. Till I entered these labs, I never made any sample. Believe it or not, I learned stoichiometric ratio only with a lab assistants in the University of Kiel. This is how I started my career in this what I call this. Since Tangadurai, when I entered, by the time he left the University of Calgary, I thought he will help me, he will teach something, but I landed with the family. I struggled hard initially 3 months. I don't know what to do. Even I'm struggling with the what I call the finding out the stoichiometric. They show how to weigh the samples and so on. So first material is because people have tried the tantalum niobium. Antimonide is the reported systems. DF is I don't have anything in mind, just I included the bismuth. Bismuth has the 3-valent and 5-valent also. I thought bismuth is 5-valent, that's why I included the bismuth in this family. I made systematic studies. So then I plotted the RNAs, I found very, very interesting aspects. So when I substitute the tantalum, and niobium, and antimonide, and bismuth, you can see the best conductivity I got it for bismuth next to the antimonide, then niobium and tantalum. Then I realized some correlation between this conductivity and this substitution. When I look into the lattice parameters, so moving from this one bismuth, you can see here, this what I call the activation energy goes down from tantalum to bismuth because bismuth has the maximized conductivity in this series. But lattice parameters increases. So when I able to, it's a cubic structure. When I able to expand the lattice, conductivity goes and activation energy comes down. So which tells me that some correlation, somehow I have to find a way to enhance this lattice volume of the cubic, then there is every possibility of increasing the conductivity in consumption. That's what my first. But we want to test this conductivity is 10⁻⁻⁶, leave it. What about the stability? It doesn't have the good stability, electrochemical stability, metallic lithium. And what is the fun in doing this research? What we did is just took the molybdenum crucibles, then put metallic lithium and heat it and melt it, that's molten state, put the sample directly in pellet and see what's happening. Very interestingly, except tantalum. Tantalum for the molten lithium doesn't react, there is no thing. But when I put the antimonide substitute samples, some within a fraction of minutes, then dots starts to happen, black dots, which tells me that the surface starts to react with metallic lithiums. Niobium completely black. But very interestingly, the maximized conductivity I got it from bismuth doped samples. Few classic fireworks inside me. I'm not an electrochemist. Just my raw hand. Just I want to test what would be the electrochemical stability. I don't have any other option in those days in 2006. So what I did like this. So what happened? What happened is molten lithiums, when I put the pellet of the bismuth doped systems, it starts to creep through the pellet and sits on the top, break into 4 pieces, and a big fire took place in the glow box, completely glow box as we. So very big. Still I'm having the video, wonderful fireworks. Which tells me that bismuth is not stable. Then antimonide is also not stable. Niobium is not stable. Then tantalum substituted thing is the only stable. And when I published these ones, lot of questions, because in Faro's case, people want to replace the titanium by tantalum, still the stability is poor. But this is the niobium, completely black. Reacts very easily. But this tantalum system is quite interesting, but it doesn't react. But a lot of question marks those days on the French group, because and the Faro's case structure, tantalum is not stable. So that's the concept behind what you call thermodynamic stability and kinetic stability. Not a lot of controversies. But I want to test further. By the time I should go to credit should go to the cousin from the Sussex, a good structural chemist. So he got a lot of interest. What he has done is instead of the border diffraction, he has gone from neutron direction to samples. Very, very, very interesting. He got results. He got it. Earlier we thought that lithium is housed exclusively in octahedral coordination. We found that lithium is housed in the octahedral and tetrahedral coordination. And very interestingly, there is a partial vacancy in this tetrahedral octahedral, which really helped me a lot to understand these ones. When I realized there is a partial vacancy, there is a tetrahedral and octahedral coordinations, and I can play a lot with these systems. I could improve the conductivity. So what I did is Li5, La3D is three. I considered four. Initially, we discussed about the four best possible combinations. This Li5 comes the next, but still I'm having a three more. So I have to cross the barrier if at all to realize I want to make these materials. So what we did is just by means of this, I just able to reduce this lanthanum, put my divalent material, increase the concentration of the lithium to 6. That's why magnesium, calcium, strontium, barium, and barium, I could get the best conductivity with the barium substituted systems. Leave it. So this is the, as far as my knowledge is concerned, this is the first material where we put the metallic lithium on both sides, and as a reversible electrode, impedance pattern has been measured with the barium. So you couldn't find the styles, which tells you it's a good lithium ion conductor. The same thing with the gold is the blocking electrodes. You can see the tile, and I couldn't see any tile. So barium doped system is the best system. It can be electrochemically stable. But what about the conductivity? Then we did a lot of work on those days. Then the what we call the Habergler measurements, the lithium blocking gold electrodes. That time itself 6.8 volt. There is no leakage of electrons, which tells you the electrochemical stability is quite good. Then what about the conductivity? So this is the raw reactions. There is no reaction with these systems. Then by the time people started to get a lot of structural information in several groups, we also proposed some dynamics of these ones. But I want to test from moving from Li5 to Li6 where I am here. Just able to cross another barrier, still to another competitors. Then is it possible still to improve the conductivity? This is how we entered into this what I call zirconium containing lithium carbons. It started from here. Then moving from the Li5 to Li6, Li6 to Li7, then zirconium, hafnium, and things, but zirconium is the best compositions. So this is how we ended up with this what we call zirconium containing lithium garnets. It's the biggest breakthrough in fast lithium ion conductors. So I am able to clear all the barriers. Now we are the number one as far as the conductivity is concerned. With the molten lithium, it's stable against or even advanced together. No other material in the world can be most stable against molten lithium like this. And we made a perfect battery and this what we call the LLZ. There is no leakage, still 7 volts. So what else is required? Maximized conductivity, good electrochemical stability, potential is so good. And we made a figure of existing systems, sulfides, antiphosphates, borohydrates, aggregates. This what we call these garnets possess the figure of merit. So this is how lithium garnets are the most attractive system for the solid-state battery is concerned. This is a story behind the zirconium containing lithium garnets. Then we want to understand, because we moved from Li5 to Li6, Li6 to Li7, if we are able to increase the lithium concentration by increasing the lattice constant, is it possible to improve the conductivity much more than that? Unfortunately, we are unable to increase it. And we want to understand what's happening between the lithium 3 to Li7. When we are having just lithium 3, lithium is housed exclusively in tetrahedral coordination. There is no vacancy. That's the reason why it becomes like a. When I increase the lithium concentration to the Li5 by expanding the lattice, what's happening? Slowly it opens up what we call octahedral coordinations. When it opens up the octahedral coordination, some of the lithium is jumping from this what we call completely filled tetrahedral to the octahedral, and I'm creating a partial vacancy in the octahedral and tetrahedral coordinations. And when I improve it, it's a perfect ideal condition. I could bring down these bonds. So what will happen? Very easy for the jumping, and activation energy comes down. And this is how I could able to improve this what we call the conductivity, moving from Li3 to Li7 in lithium garnets. Then good enough got interest. What he wants, what is the optimized concentration of lithium? The 6 or 7. Then we are able to find out something on lithium 6.4 to 6.6 is the ideal composition to get the maximized lithium ion conductivity in these systems. But afterwards, I don't think you will be in a position to improve the conductivity. There's no meaning in working. So I made this invention in 2007 from Kiel. I came back to India. Immediately, I got the job, what I call the Director for Science and Technology. Then I'm so happy because it's a very powerful pollution control board, science and technology, coastal zone management, and something else also. But 2007 to 2010, nothing no development. So when I published this paper, I just included the Professor Tangadarai also, but he was setting up the labs. He also struggled to make these materials. He failed it, so he lost the confidence. Since I didn't do any work for the next 3 years, nobody in the world is in a position to produce this material, and a lot of controversy arises. Then really I was so surprised. I struggled 8 months to make this material, and this is my what I call the gift to my Professor Werner Epner on his 65th birthday during his retirement. Just I announced these results on his birthday. He published in Angewensche Kenning. But later, nobody in the world is in a position to reproduce materials. Mostly they end up with what we call tetrahedral structure. I never realized we were having a one more structure in lithium garnets because all the garnets wanted a cubic structure. But Japanese group realized at 980, mine is 1230, able to make this material 980. They told that it's a tetrahedral structure very badly. The conductivity is 2 orders of magnitude lower than mine. The world is looking at me about my results. This forced me to resign my position as the director for science and technology. I resigned. I went back to Toyota. Then we understood what is the reason behind this. I am able to make this cubic structure and why all the people failed. They could make the tetrahedral structure. The story is very simple. So God favored me. So I used to prepare this material with alumina crucibles, not like the other people, platinum, other things. So when I used to put it for this 36 hours in a particular furnace, 1230 degrees Celsius, from the alumina crucibles, aluminum entered into my pellet and replaces some of the lithiums, then aluminum sits over there. That's the reason for the incorporation of the aluminum and reducing the lithium frequency very close to 6.6. When it changes from the phase from tetrahedral to the cubic, then I could improve the conductivity. I used to get 10 power minus 4. But others unable to incorporate the aluminum and unable to reduce the lithium concentration, they end up with this tetrahedral structure. This is how in 2010 we realized that everybody understood mechanisms. Then we did. So we want to still increase the conductivity by means of reducing the grind boundary resistance, like what we call grind boundary engineering. We introduce this concept of what we call lithium aluminum silicate, partly crystalline and amorphous phase at the grind boundary, and able to reduce this grind boundary resistance, still able to improve the conductivity. It's quite good. So now the conductivity is so good, potential stability is so good, then people started. Then still we worked in here, they putting lithiums. They are able to bring down to 10 power minus 3 Siemens per centimeters, which is competitive with the liquid electrolytes. Then people started to ask, so you're able to make this material good stability against metallic lithium, and potential stability is so good. Then this could be ideal choice for lithium ion battery, lithium redox flow battery, all solid state battery, everything. Then why don't you make a battery and test it? This is how we started this item. We used a PLD for lithium cobalt oxides, sputtering for the what you call this making the other things, thermal evaporation, this lithium inside the glow box. Then what you call we make this is the first all solid state thin film lithium batteries based on what you call lithium carbonates in 2010. If you ask me, the result is very, very, very poor. Believe it or not, the lithium cobalt oxide LLZ and metallic lithium, I am unable to glow even a LED. It's in microamps, not even a milliamps. So we understood. People thought that able to find a suitable material, immediately they can fabricate the all solid state battery because technology has been demonstrated life on. But they are having difficulty in making this scaling up this life on. That's why they couldn't. The CV. So our success story is, I think we thought we will success. We failed in the first attempt in 2010 at the Toyota. That's the time whole world is picked up this. Then people start to understand what would be the challenges in solid state batteries, particularly lithium garnet based batteries. Because liquid solid interfaces God is fabric. The conventional liquid is conventional battery. But when you have a solid, physics knows very well that solid interfaces are really tough to crack. The biggest problem is the interfacial challenges. Particularly anode sites were having uneven lithium depositions. side reaction with the what you call the cathodes, and poor contact with the solid-solid. When I want to use the lithium, then what you call dendrite is the biggest issue. Still, we thought that solid ceramics will varigate the lithium penetration, what you call dendrite. And still, I could see through the grain boundary, I could see the grain needles forming. And short circuit takes place, and high shear modulus and electron conductivity, several things people start to understand with the dendrite. And cathode compatibility is a much bigger problem. Diffusion of these cathodes and what we call the reaction product layer and space charge layer, impurity, the lattice mismatch is other part. Because we thought that ceramic processing is easy, but garnet also started to give trouble. And moisture stability is poor, the thermal stability, the mechanical properties, oh, so many problems, which means that other than after finding a suitable material, still we're having a big technological drawbacks. How to overcome this one by one. So this is how we're spending for the last 10 years to overcome these electrolyte interface. So if you ask me, initial stages, early engineering stages, applying external pressures and heating lithium metals. Then later we started with the interface engineering, surface microstructure design, surface policy, changing the chemical compositions. Then we entered what we call artificial coating layer between the electrode and electrolytes. We used a sputtering, plasma and gas, vapor deposition, ALD technique, and operation. So many techniques, because several people started to do research on this one, and slowly, one by one, we could be able to resolve these issues. Imagine this is the dendrite growth and large electrode interface of the anode sides. So lithium is highly reactive. Whenever there's a small gap in the grain boundary, it starts to penetrate. You can see here, then like this, then this one. So a lot of theory came into the pictures. What's the reason for getting this dendrite growth in the solid lithium ion conductors? That people realize uneven current distributions. And people started to introduce some buffer layers, whether it's a metal oxides or the non-metals, and polymeric layers, and so many things people have done it and able to overcome this interfacial resistance. At the same time, they're able to overcome what we call dendritic growth. This is our earlier research. We're able to put this small layer of this metallic lithium, gold here, between the metallic lithium and the lithium garnets. It's what we call thermoport lithium. There's a large gap. When you put this, we can hear. But when you're able to put the gold layer and sinter it, I could see some gold lithium metallic alloy has been formed, which is really helped a lot to reduce the interfacial resistance. At the same time, it able to improve this what we call critical current density, which means that it's really helped a lot to overcome the what we call this dendritic growth. Now we are having several techniques to overcome the issues with the anode and lithium garnets. That's what we call the people are using atomic layer deposition, sputtering technique, and wet processing technique, thermal operation techniques, polishing technique, heating techniques, and acid treatment technique, and so many techniques are available. By this way, they're able to decrease this what I call remove this interfacial resistance or decrease the resistance. Even people started to report 1 ohms per centimeter square is the interfacial resistance between the lithium metal and lithium garnets. Believe it or not, we thought that it's impossible to get the interface like the liquid and solid interface, but this solid-solid interface, because of this interfacial layer technology, what it did, we able to get the 1 ohms per centimeter square much better than what we call the liquid-solid interface. So if you ask me, I could say almost all the problems regarding this lithium metals and lithium garnet interface is solved. People have done huge amount of contribution for the last 5 years. But you can ask me, what's the major problem at present? Biggest issue is the cathode garnet interface, because that's our trend. If anybody does some research, whole world follows the same thing. Everybody worked on the lithium metals and lithium garnet sides. They've forgotten the cathode problems. Now, other than the anode sides, cathode sides is the biggest issue now. If you ask me what are the issues, poor contact, space charge layer, lattice mismatch, volume expansion, contraction, elemental code deficiency, formation of reaction product line. Oh, that's what we have. I'm writing a review article on this topic. It's huge, and people accept. I can give a classic example. Why this reaction product line? Because this, what you're having is the lithium cobalt oxides as a cathode. This cobalt very easily diffuses the solid. So after a few charge discharge cycles, what happened means this copper diffused to the lanthanum sites, and whilst this what you call reaction product line has been found here after a few cycles. Start to give a large interfacial resistance. That's a problem. This is an in situ measurements. We observe that. So this garnet and the lithium cobalt oxides reacts very easily after a few. Then it forms the reaction products, suppress the cycle efficiency. So we realize this should be overcome. Then we have done several work throughout the world. People have done a lot of work regarding this. This is another way of overcoming this. So just by means of this point conducted core interface, area conducted improved interface, then you can see here. Without lithium silicon layer and with lithium silicon layer, we introduce one layer lithium silicon and put this what I call the LCO. Then its binding is so good, then able to give the better cycling efficiency. But I don't think it can match with the present day liquid electrolyte battery. That what I call interface is not so great. We are able to. Slowly we are improving on the cathode garnet interfacial issues are concerned. So you can see the battery performance with what I call the lithium silicate interlayer. We are able to improve it when compared to this without lithium silicate, very poor, but we are able to show a few cycles. Then quasi solid state battery, people started to use the gel interlayer here and here, anywhere. So able to improve this performance. So people are working this at present, the glassy interface between these cathode and garnet is highly optimal. But much more interesting, we are living in the world of cathode light. So just mixing with these ionic salts with what I call the composites cathode, then you can make a toothpaste like this, just you paste it, then sinter it, then bonding is quite good, then high temperature starts to melt and slowly hot. And polymeric composite is another example. Put the mild polymer at the interface with the cathode and the lithium garnets and just go for thermal process and make a perfect bonding. So at present, people are working with the catholites. By the way, they are able to improve better contacts and really they are improving the cycling efficiency. So as far as me is concerned, people have improved dramatically the production of lithium garnets. Already ceramic processing technology is matured. So we're having several techniques starting from the cast technique, film casting technique to the roller casting techniques and tape casting techniques. People able to make the 50 micron thickness of garnet tapes, a few meters or 50-meter tapes rolls also visibly I could see from the industry. Very good reasonable conductivity of 7 into 10 power minus 4 seconds. This is the dream of solid electronics. Like a separator, they want to see these tapes with good conductivity, with very thin things, 50 micron. People are working for 30 with the other groups also. And few meters. The logical production is quite good. Almost removed all the obstacles. Then anode sites, lithium metals, then able to improve this lithium and the garnet interface as well. Developing beautiful technology, just the processing of lithium metals. Even if what you call 20 micron thickness and 5 micron thickness of the lithium metals make it within a few minutes with a large surface area. It's almost solved. Then now it's time for the cathode garnet interface. But told you what I call cathode light technique is the ideal technique people are working in a lot of industries. So not only lithium metal batteries, lithium sulfur battery also we have done. You know very well that lithium sulfur batteries, the energy density is almost unimaginable. So you can see here, 1000 watt per gram is possible. Moving from lead to lithium ions, lithium sulfur. But where people working in lithium sulfur battery realize how difficult it is, what are the major disadvantages? So lithium ion and lithium sulfur. Biggest problem is the complex working mechanisms. With intermediate species. Oh, that is the biggest bottleneck. People struggled hard. If you ask me, everywhere we are having from cathode, low sulfur conductivity, dissolution of active material, passivation of instability, LiQs. In the electrolyte also solvent polysulfate reactant, subtle mechanism, viscosity variations, and anode mossy lithium unstable interface. That's why this initially took very big leap, then slowly it's coming down. Again, if at all, if you want to improve the performance, we have to think about making a solid electrolyte. Do this, we made this LLZ membrane, and we are able to demonstrate somehow we are able to barricade this what we call this shuttling mechanism with solid electrolytes. but it's a very thick. That time we don't have the membrane like what we are having present day, 50 microns. Then we coated this LLZA on these polypropylene substrates. Then we could improve it. But still, we're working hard and we're looking for something else to present 50 micron because garnet films, how to improve this performance of the lithium battery. We are working. So what I can conclude in these passions. So initially, we are living in this world of present technology of the cathode, graphite, and liquid organic polymer electrolytes, and what you call, cathode is a lithium carbon dioxide, or lithium iron phosphates, or NMC and NCA, and organic polymer electrolytes, and lithiated carbon. This is the present technology. Almost 40 years we are surviving this technology. Then we propose this all solid state battery. Just you can reduce the thick volume by 38%, replacing carbon, high frequency of 50 to 20 micron of the metallic lithium sufficient. I could think about of making the solid state lithium. A well-known demonstrated techniques. I don't require anode-free lithium batteries. This has been demonstrated live on. Might occur in just long back, 20 years back. So what you require is the lithium. Just I can what people are present with all the startups, big startups, where they got huge money from all the big people. So what is the technology is something different. So they just want to have the cathode, maybe NC or NMC. In addition to that, putting a catholyte here, then adding another substance. This is what we call the high lithium content substance. So just plating the lithium on this anode sides with the current color, the solid electrolytes. So which means that metallic lithium is plated through these ones. Which means that the biggest problem people face with the industry is how to handle the metallic lithium, how to get this thin layer of metallic lithium. Oh, very difficult. Now things are completely changed. This attitude has completely, strategy has been completely changed. Pushing lithium from the cathode sides and making a metallic lithium at the anodes and during the plating. Very interestingly, people have observed that it's not like a vertical, this vertical side, it's perfectly forming a 20 micron or 30 micron metallic. Then it goes back to these other sides. Shuttling mechanism takes place, people are able to slowly improve because what we required is during this plating, this electrolyte should be stable, there should not be any fracture. Again, during flooding, this copper current conductor should not be fractured. So people are working hard how to improve these things. By this way, once we are successfully demonstrated, but still it's foreign. I think putting a catholites and composite electrodes and this what we call lithium-free electrolyte, lithium-free battery. So plating, you have to make it on the other sides. So this is by this way, you can reduce this what we call volume by 50%. Just imagine. Metallic lithium, you can improve the energy density by what we call 10 times. Still, size you can able to reduce it by means of these techniques, what we call anode-free techniques. Then imagine how much you can improve energy density. So this is the biggest advantage of this what we call solid-state battery, which helps to enable lithium metal as anode, enables high voltage cathodes. If you combine together, then smaller size with high energy density. You cannot imagine anything else in the world because lithium is the lowest reduction culture. There is a ceramic layer, then not operating temperature range. Don't think nothing will happen even if you go to 200 degrees Celsius. 180 is metallic lithium melts, so 150, 160. Then it's nothing but a solid. We expect the lifespan is the lifespan, electronic portable materials, devices. Lifetime of the portable electronics is the lifetime of your battery. And above all, increased safety, although you're using metallic. So these are the greatest advantage of the solid state battery. That's why we are able to make this one. That's why a lot of this activities, a lot of money has been poured in big steps, and everybody is focusing on it. So with this one, I wish to wind up. So I should be grateful to my also Varna Hapna, initiated with this of German Science Foundation. We should go to my friend Priyama. Initially, Suzuka University, later he moved to the what you call Nagoya University. I just want to teach. It should go to Professor Brenda also, who invited me just to and I should be thankful to most of the contributors and my co-workers. Made these things also possible in part of India, southern part of India. With the applied materials, really helped to develop a big lab huge money. And Fisker also did some consultancy. Learning, CSIR, UGC, DRDO, DST, TAEBRNS, AICTE, BRNS, almost all the agencies. And now we are entering into this one called HPL power system. They are true battery makers, indigenous battery makers. Because almost all the 80% of defense applications made by this battery. I'm impressed with this one. Just we join hand with the HPLs, making a big leap. So I think it's possible in India also. One day we can realize this all solid state lithium batteries based on lithium. Thank you very much for listening to me. I should be happy to answer to or interact with you.
Thank you so much, Professor, for a wonderful talk. Really amazing talk. Audience, if you have any questions, please.
I think large crowd, almost 100 people it seems, more than 100 people.
Yes, sir. Yes. Audience, please ask questions.
Still, Mayalagan is there or left?
No, I'm there. I'm here, sir.
But I took longer time or it's okay?
It's okay, sir.
It's on time, sir. No
It's
problem.
on time.
So I have a
Another
question,
15
sir.
minutes.
Yeah, I have a
Yeah, please.
question. For sulfide-based solid electrolytes, as you have discussed, it is really challenging to get a stable electrolyte at ambient conditions.
Just can you repeat? Sulfide?
Sulfide-based solid electrolyte.
Yeah.
Like how we can make it stable at ambient conditions? Like can we do doping of some transition metal oxide to make it stable at ambient conditions?
No, it's very, very difficult. I can say it's impossible. That's why I told. It has all the characteristics. But my thumb rule is what I understand for the last almost 14 years of my research battery. If you have one or two good properties, certainly you will have other diminished. It's very, very, very difficult to get the sulfides and process it at the ambient conditions or the open air conditions. And whatever the results they are getting in the button cells, coin cells, they cannot be in a position to reproduce when they move to the what you call the pouch cells. Imagine, that's why Toyota is spending huge money, but still, when you go for bulk production, even electrolyte conductivity has come down again. That is the biggest bottleneck. Other things, compatibility is fine. Just like that, you can make a battery, but very difficult. People are struggling hard just to realize the production of these electrolytes. It's impossible. You have to, because you know very well that sulfide. It's impossible to make it at the ambient conditions. But it has wonderful characteristics. Absolutely. But people like they are also started to work. Other directions, we don't know where we are going to end up, but it takes some time to realize it. Yes. What about others? I think all the people left or only we four are there?
No, sir. They are there.
No, sir. But yeah.
102 people are there, participants.
Yes.
I think I will ask another 15 minutes. Since I am in the Pondicherry, I put the beach. So don't think that I am sitting next to beach.
Hello, sir.
Yeah, please.
Yeah, I am Sendal Ram, sir. I'm your student long back.
Sendil Ram, can you show your face?
Just a moment.
So when did you join here?
I'm with a private organization. I joined the SRM as a part-time external candidate.
Oh, it's good. Still you are working with the magnetic company or you switched over?
Magnetic, not only magnetic materials, materials for all other applications like starters and starters alternator, belt starter generators, where we do we also make electric vehicle motors. So apart from the battery is one part where we least use, but the thing is that we also interested in going to battery technologies in future. We are actually application usage. We are at application usage where we buy the materials from our from third parties. So I just wanted to know, like, what is the voltage rate the battery can withstand?
It depends upon what type of electrode you are going to use it, first of all. With the people, what we are having comfort with the lithium cobalt oxide and lithium iron phosphates. You know what is the limitation of those two electrodes. So it all depends on what type of the electrode you are interested in. It's going to decide about the voltage you are going to end up.
Okay.
But this battery, what you're suggesting is not only we can stop with this NMC, NCA. If someone makes a battery cathode which can go up to the 6 volts, then we can use it. So it's give a wider option because the present electrolytes were having difficulty with NMC and NCA. But decomposition takes place. But this solid electrolyte can withstand this much larger decomposition. So you can, anyone makes a cathode which can go up to 7 volts, still there is a possibility of using these materials. So there is no end at present. With the existing batteries, with the cathodes, any cathodes we can survive with these ones. I don't think chemistry is not going to change as far as solid electrolyte is. Am I correct? Still I couldn't understand what you expected, what Hans said.
We are working with 360 volt machine, induction motor, that goes into four-wheeler electric vehicle. Okay, so now for this.
So our ultimate aim is to get a 360 volts. How many batteries you require? What would be the volume you require? That we want to reduce it dramatically by means of your solid state battery. At least 50% reduction. Yeah. And moreover, we don't require a battery management systems. We can still reduce this. So which means that smaller in size, you can get this very easily 360 volts to operate your electric vehicles. Means that you can have much more. So which means that you can put larger amount of battery. So you can think about the longer run also, increase the mileage also. That's the idea behind of going towards these high energy density batteries consumption. Voltage, we don't have any problem. Like what you are doing it, we can improve the voltage, increase the voltage, whatever you find.
Okay. So our project is very preliminary. We are now started our design for this 360 volt, which is high voltage.
Good, because we are having a national mission is coming up. Dr. Mayalagan is also one of the members. We are having a separate topic about the motor section with Hyderabad, ARCA and metallurgy. We are having one institute in metallurgy. They are also partners in making these motors. We are having a mission, national mission for the electric mobility. We are having a separate chapter for what you call these electric motors.
Okay, sir.
You are getting it in another 1 month time.
Okay, sir. I request you to forward an invitation.
Yeah, that's we can.
Yeah, so that I can involve my organization.
Oh, good. It's okay.
Actually, our organization is Sona Comstar Automotive Technologies. We are into development of this hybrid powertrain machines, like starter. And
okay, we can discuss. I think we can give a chance to others also if anybody is interested.
Yeah. Maybe I will get your contact.
Okay.
Thank you.
Anyone else?
Hello, good evening, sir.
Yes, please tell me.
Sir, I'm Dr. A.B. Lateef. I'm working as a postdoctoral research associate, and I'm working in electrochemical sensors. So, if you don't mind, may I ask some regarding if you have any expertise in electrochemical sensors?
Yeah, this basically, if you have an electrolyte, then you have to this where I work with solid state ionics and sensors.
Okay, sir. Thank you.
So Webner is expertise in sensors, not in the battery.
Okay, sir. Thank you. Thank you very much. So basically, if I want to fabricate an electrochemical sensor, basically we are modifying an electrode to develop an electrochemical sensor. So I am bringing two moieties together, like two metal oxides or conducting polymer and metal oxide. So while fabricating this electrocatalyst, so what is the criteria that we should bring two particular moieties together to develop a very good or highly sensitive electrocatalyst, or we can do it randomly? I mean, am I able to choose any kind of material to develop a nanocomposite, or I should take some criteria while choosing my materials?
No, it all depends on what type of application you are interested.
No.
Yes. Again, anybody?
No, it depends on what type of sensing material you want. And also conductivity is also important.
So a best example, oxygen sensor. Still, zirconia is the best sensor. But if you go to tin oxide, it has its rapid response. For some application, it requires some rapid. So depends upon the what type of sensor is, depends upon the what type of application you are interested. So carbon dioxide sensors feel that this lithium carbonates and this what you call lithium ion conductors could help. So the carbon dioxide sensors were depending on this lithium ion conductors. So it tell me which sensors. Then we can decide all the things it's going to decide.
I'm interested in the sensing of biomolecules, especially.
So biomolecules, then I don't think this will be in a position to use. But again, it depends upon these things. Most probably these oxides may not be that much so fast response. I don't know much idea. Others can give. Maybe experts can give.
Okay, sir. Thank you.
So, sir, there is a question from Ajay Pratap Singh. In near future, is it possible to replace traditional batteries by solid-state batteries?
Pardon?
In near future, is it possible to replace traditional batteries by solid-state batteries?
I couldn't get exactly what.
No, is it solid-state batteries can be the near future? We can replace the traditional batteries.
It is the need. Whether we like it or not, it is the future. Whether we like it or not, it is the future. The amount of money, because like a vaccine. Because the last 100 years, whatever the vaccine, the money they spent, they couldn't make it because almost the pandemic is over. That's why the huge rush for this COVID pandemic. Like that also, the solid state battery, the amount of investment people throughout the world is huge, huge, huge. So whether we like it or not, they will push it. The day is not far away of realizing the solid state battery concept. This is what is my conclusion. Absolutely, it has its large characteristics, huge advantages. Certainly, it will be a future. Still, I can expect few more questions. So many people are there.
Good evening, sir.
Yes, please.
Sir, I'm Dr. Tanuja from Sairam Engineering College. So, actually, lithium batteries are there. So, lithium having more diagonal relationship with magnesium. Is there any possible to do with magnesium? Sir?
Absolutely, because we are working on several aspects. So, people are working on magnesium, calcium also. So, while we are focusing on lithium is highest energy density is possible with lithium because we cannot find any other element to highest energy. So, with the smaller in size, I can get the best energy density. If I go for magnesium, the chemistry and so many things is not that much mature, it will take longer time. Certainly, energy density is not going to be so good compared to this. Absolutely, it depends upon the, let us take the grid storage. It doesn't require, it doesn't depend too much on the what would be the volume. So that type of applications, then you can think about something bulk material, bulk batteries also. So you can focus on. Somewhere you can find magnesium where you are having a lot of magnesium, resource is so good, so I don't want to import something, then it's a possibility. But we are pushing this lithium for electric mobility. I want the reduction in weight and size than longer run, so longer mileage. Lithium is the best option. I can make a very thin battery. So whatever the size we are having, let us, it's, I think 1/10, I can reduce the size. And I can put 10 batteries. So naturally, I can improve this dramatically. That's the idea behind this lithium battery research is okay, this magnesium also one day it will come. People struggle hard with the calcium battery, the cheapest materials. So it all but naturally, the energy density is the biggest question. Sodium battery is the classic example. One of the cost wise it's less, but if you look into this technology, if you really want to make it, then you have to spend huge amount of money. So whether people like it or not, I always used to say this battery research is very simple. If you feel this is the low cost and it is still available, certainly it will have the major disadvantage. It cannot compete with the right technologies. So you have to overcome. But I don't bother much about the energy density. But with the existing materials, I don't want to depend on other countries. Then the classic example, sodium is the battery, magnesium is the classic. You can focus. But it will not replace like the what you call iPhone. I don't think, because that's standard. You know what are the characteristics of the happily is concerned. It's very difficult to match. So over guys, they always think about what is the modern 4G. If anyone uses a 4G, they will not come back to the 3G. So the commercial market trend is like that. So people will be behind these lithium batteries for quite a long time until to find any other technology which can beat the lithium-ion battery technology.
Thank you, sir. Thanks for a nice explanation, sir. Really wonderful session, sir. I learned a lot in the session. Thank you, sir.
Anyone else? So I'm very happy to hear that SRM University also stall was at that energy. So Murugan is one of my good friends, and he is trained by the Mandiram, and he is also doing woodwork, and many people are doing woodwork. I think day is not far. This is what I used to say. So somehow the breakthrough comes from the southern part of India, particularly from Tamils. So maybe I will live for some more years. I should realize that it will happen. New technology or new things. Because the amount of money spent by the quantum scape with like this, as I talked to a day before also with the quantum scape scientist, particularly friend my Ram. Microsoft, I think the Bill Gates, how much money he's put in for the quantum scape based on just garments. They're having some 27 patents on garments based on my material, just tantalum and aluminum. It's a question of they already made a simple cells. Now they are worrying, their focus is on the stacking. So if the technology really helps to make a stacking, I think the technology of this lithium platings and lithium free and the catholite and the composites and putting some extra lithiated things in the composites of cathodes, I think it's wonderful. I think that really they got a good they made this. And also they understood this fabrication of these tapes. They are making 13 microns, conductivity of 7 into 10 power minus 4. It's really wonderful. That technology is really helped them a lot to move forward. Believe it or not, we don't have these technologies. We are struggling hard to make the tapes, 100 micron. So really their expertise and experience really pushed things. But anyway, India also one day will flourish.
Yes, sir. Thank you so much, sir, for your wonderful talk.
So I'm very happy. First time I am seeing more than 100 people in the when Murugan approached the webinar.
Okay.
I told him I never give talk in webinar.
Okay.
I had a principle like that because I had the pandemic starts when I have a very bad thing with my international conference. That's why I'm not interested, but I'm very happy to see 100 people are listening. Still 82 people are there in this webinar. So I'm very happy being with the part of the faculty members, but a one-to-one interaction is not possible. You know, I'm so happy that I could interact with more than 100 faculty members or the business scholars. Thank you very much.
Yeah, thank you.
Thank you, sir.
Thank you very much.
Participants, tomorrow we will start the session by 9:15. You please log in. Tomorrow at 9:15, please log in. Thank you.
Thank you.
We will meet again tomorrow. Thank
Thank
you,
you,
Dr. Murugan.
Thank you, Kamala Bharat.
Thank you.
Thank you.
Sir.